And right now we have Anova. Okay, so let's start. And I'm going to share my screen with you guys. So all the documents have been posted on Canvas, and great, good. I have it here. Okay, so let's take a look at Anova. Okay, so the first thing is we have to know what Anova stands for. And if you watch the video, you probably know it. So Anova stands for analysis of variance, right? Anova stands for analysis of variance. Do you remember why? Where does the variance come from? Where does the variance come from? Why is it called analysis of variance? If you watch the video, you probably see some kind of a table like this. Where does the variance come from? I mean, what do I mean by variance here? What exactly is the variance? Who wants to give it a try? If not, do you remember anything about it? Hopefully you remember this table, right? Okay, so I'm going to answer it here. So the variance actually comes from this word, variation. So to answer this question, when we try to set up Anova, which is a test, when we try to set up this test, we have to establish this table. And this is the table. How do we set up this table is, we are going to consider different sources of variation in your data. So why the observations you collected from your data are different. So we're gonna split the source of variation in your data, in your observation, into largely two components. So that's the between treatments and then the Weizen treatments. If you remember, those two add up to the total, right? So this is where the variance of variation comes from. Okay, so it is important to notice that Anova here is a test. It's only applicable for numerical data. It's only applicable for numerical data, and we're going to use them when the number of populations is more than 3. Okay, what are we going to do if it's less than 3? For example, if it's 1 or if it's 2, what kind of test are we going to do? Do you still remember that part? If it's numerical data, if the number of population is 1 or is 2, how are we going to do that? Who wants to give it a try? We have already talked about this last week.
You use a paired test or test of independence for 2 population?
Yeah, 2 sample test. It's going to be either 2 sample test. If it's a 2 population, that's going to be 2 sample test, right? We talk about it's going to be 2 sample Z test or 2 sample T test. If we do have some kind of a paired or matched test, it's going to be paired T test, right? Excellent. Okay, and so the kind of Anova test we are focusing on in this class is called a one-way of Anova. And the reason for that is because there's only one factor. If you watch the passenger class, the satisfaction of the airplane passengers example in this week's module, you probably remember there's only one factor there, even though you have 3 different groups or 3 different classes, or some other textbooks call it treatments. You have the first class, business class, and also economy, right? So 1 factor, but 3 treatments. Okay, so we are focusing on one-way Anova. There's also a two-way Anova when there are more than 2 factors I consider, which is beyond the scope of this class, but you can easily see the same kind of a table we can set up for two-way, right? Okay, in order to carry out Anova, the most important thing is to set up this table. Once you have this table, our ultimate goal is to be able to figure out this number here, this particular number, which is F ratio. This is what we're gonna do, right? Okay, and in today's meeting, I'm gonna talk a lot about how we can set up this table and how we do that. Okay, so I'm gonna write down several things which is missing from the PowerPoints, and we want to go over that together, right? Okay, so the first thing is you have this table. It can be split into 2 different sources of variation, the between treatments and also the within treatments. If you are thinking about a flight passenger satisfaction example, between treatments, that's gonna be why the observations are different because they are receiving different treatments. Some of the passengers were put on the first class, some of the passengers, they are economy, right? So that's why between treatments, they are receiving different treatments, and some other book or maybe software call it model. So this is the variation that comes from your model. the observations, the passengers certainly are going to be differently satisfied because they are actually receiving different treatments. Okay, and the sum of the squares for this part is going to be called the sum of squares, as you can probably see. So sum of squares, so 2s here. What is this part called? Do you remember? It comes from
SSTR.
Great, Rachel is correct. SSTR. Okay, excellent, excellent. So the next one we have is Weizen treatments. So this is also known as error. The reason we want to think about it here is even though all, say, 7 passengers were all on the first class, but they still assign different satisfaction scores. And the reason is because even though they're receiving the same treatment, but there is a person-to-person variation, right? Even though we receive the same treatment, we may have different standard, different expectation, we might assign different scores. And the reason is because we are individuals here, we're gonna be unique, we have different preference. So that's why we're gonna assign different scores. And this is gonna be the part that's gonna be considered error part, right? Error part, okay. And do you remember what is this called? SS, who wants to give it a try? This is actually not too difficult to remember. If you see the error starts from E. So this is actually called SSE, right? Okay, so the total is actually SST. Okay, I'm gonna write out the number 1 equation, relationship we're gonna talk about today. That's SST is always SSTR, the sum of SSTR and also SSE. So this is super important. What I also like to emphasize here is as far as this table or maybe Anova test is concerned, formula tables posted on Canvas do not contain any information for this module. Remember, you can take, you can bring a note card for your final exam, or maybe when you were working on assignments, you definitely want to make sure whatever information we're talking about today is going to be placed on your note card, right? At least you have to be able to find it. I mean, otherwise you can also memorize everything, right? Okay, so the next column we're going to talk about here is going to be the degrees of freedom, right? Okay, so there are going to be 3 degrees of freedom here that are going to be corresponding for the model, corresponding for the error, and also the total. Okay, so I typically like to start filling in this table from the very last part, so from the bottom of it. So this is SST. Do you remember what is the degrees of freedom here? Anybody wants to give it a try? This part is actually not too difficult. Who wants to give it a try? So in order to fill in these blanks here, we probably have to define a new number, a new symbol here. That's an N with a subscript capitalized T here. This represents whatever total sample size or maybe objects or passengers you have collected using your data. So if you collect the 7 from the first class, 7 from the business class, and another 7 passengers from the economy, 7 plus 7 plus 7, that's 21. So N capitalized T, that's going to be 21. Once you have that number, that's going to be related with this cell. And that's actually nothing but NT minus 1, right? Okay. So what I typically like to do next is to fill in this degrees of freedom right here. This degree of freedom is going to be related with a quantity K, where K represents the number of treatments. Okay, I'm going to write down here, number of treatments. For example, if we were talking about the passenger satisfaction example, you have first class, you have a business, you have economy. So K for this particular example, that's going to be 3. Once you have K equal to 3, you can fill in this cell. And that's nothing but K minus 1, right? Okay, so how am I going to fill in the cell here, right here? How am I going to do it? So if I know it is a K minus 1 here, I do not know what the quantity here is, but I know this is a NT minus 1. How am I going to fill in here? So there is actually also equality relationship between those 3 numbers. So this one plus this one equal to the sum. So similarly, if we do want to have the cell right here, the degrees of freedom for the error, all you need to do is going to be the sum, subtract this one, right? So the difference between those 2. Okay, so if you do the subtraction, it's going to be nt minus k. And the reason is because the one here, it got canceled out with this one, right? This one, they got canceled out. Okay, so mean squares is nothing but a ratio between the sum of squares and the degrees of freedom. So it's going to be sum of squares divided by the corresponding degrees of freedom. That's mean square. I'm going to quickly write it out, and you probably have already seen it before. So the first thing is as MSTR, because this is for treatment, right? For treatment. Okay, that's equal to SSTR over K minus 1, right? K minus 1 is the corresponding degrees of freedom. Similarly, for here, it's going to be MSE equals to SSE over NT minus K, right? Okay, we are almost there, almost there. So the very last thing we need to do here, okay, yes, yes.
Yeah, so I had a question about the homework. It didn't give K, and so
Didn't
how would
give
you
K.
find the
Okay.
degrees of freedom if K is not given?
Okay, okay. We can go to that specific example you were talking about. Typically, it's gonna depends on the setup. For example, if it's a passenger flight example, we have 3 classes. That's gonna be 3 minus 1. That's 2. So I'm not exactly sure which exercise you were referring to. If K wasn't given, is it possible that maybe those 2 cells were given, and you can use their difference to figure out this one, and then you're gonna add 1 to get a K?
Yeah, I got you now.
Okay, does it answer your question so far? But I can go into look into the question 12 later.
Yeah, no, you answered my question. Thank you.
Okay, okay, good, good. Okay, and so let's go back to what I was talking about. We are almost done with the table. So setting up the table, the only reason we are doing everything so far is we are so concerned with this test statistic, the F ratio. That's what we want to do. Okay, so F ratio, the reason it's called F ratio is because we have to calculate a ratio, and the ratio is nothing but the difference between those two. I'm gonna write it down here. F ratio equals to the ratio MSTR over MSE, right? Okay, and the reason it is called F ratio is because this actually follows a F distribution, right? I'm gonna write it down here. F distribution is slightly different from what we are used to see. The reason I say that is because F distribution has 2 sets of degrees of freedom. That's a little bit confusing. Typically, T distribution chi-square, they only has 1 set of degree of freedom. Over here, we have 2 different degrees of freedom. So the first one, the second one. So the first one is gonna be the numerator, right? The numerator. Where does the numerator come from? So let's take a look. So F ratio has a numerator for MSTR. MSTR has a corresponding degrees of freedom K minus 1. So I'm gonna write it down here. It is a K minus 1. So this is your numerator degrees of freedom. So the next one is gonna be the denominator degrees of freedom. Now, hopefully you're able to see here. So denominator is MSE. MSE has a corresponding degrees of freedom, N capitalized T minus 1. So I'm going to write down here, minus K, right? So once we are able to figure out the F ratio, we can use either our F table or maybe software to figure out the P-value, right? I'm going to just write it down here. Okay, so it's going to be either a F table or maybe a software. It could be Excel stat. If you watch the video, we were using stat graphics, but typically they give you the same p-value. I just want to remind you again. So if you are looking up the p-value using F table, it's only an approximation. Sometimes it gives you a range, not an exact number. But if you are using software, maybe Excel stat, it's going to space out an exact p-value. So that's fine. We don't have to worry too much about it because all we care about is whether this p-value is greater or smaller than alpha, which is the significance level. That's all it matters, right? It doesn't really matter whether it's really, really small or maybe quite small. it doesn't really matter in that sense. Great, great.